Alrighty, folks. So moving on to the third and final lesson for Chapter 11. Okay, still talking about electric fields and voltages and potential differences and all that. Just going to look at some new concepts associated with them and new applications of the same ideas. And really, they're not that new, just different terminology and things to think about. All right, so we'll start out here by talking a little bit about a scalar field, something we have actually already talked about, okay? We've been talking about fields a lot. It's just that for most of this, we've been talking about a vector field, specifically the electric field, okay? So remember, a field is just a mapping out, essentially, of an area with respect to some quantity, right? We look at an area, and at every point, we can assign a value or think about or calculate a value for that quantity, okay? If that quantity is a scalar, then we are dealing with a scalar field, okay? So up until now, we've been talking mostly about fields that are associated with a force, right? The electric force that a 1 Coulomb charge would feel if placed at that location is the electric field. So that's a vector field because it's associated with a force, right? But there are scalar fields as well. I mean, we talked in the previous 2 lessons ago, I guess, about like how the weather map that you see on the news, that's kind of a scalar field, right? It's showing you what the temperature is like at all those different locations. Here's another temperature field, right? All it's doing is mapping out this area with respect to some quantity. That quantity being temperature. And of course, temperature is a scalar, right? Temperature is essentially a measure of, well, technically it's the average kinetic energy of the particles, right? But it's a measure of like the thermal energy, right? So it's hotter here, cooler, 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 right? But still, what it's showing us is at every point in this area, right, what would that quantity be like? So it's a field. It's just a scalar field because it's talking about a scalar quantity, temperature. Now, the most commonly type of scalar field you'll encounter in physics are those associated with potential energies, right? We know energy is a scalar quantity, so if we map out potential energies in an area, we're mapping out a scalar field. But again, it's the same idea. We're just assigning a certain amount of potential energy to all the positions in an area, in a volume, right? And that is a scalar field. Okay, a potential energy field, essentially. So what we do is we compare the potential energy reference to some other arbitrary zero value at various points, okay? Now, let's break that down a bit. What does that mean, okay? Because we know the thing about potential energy is that it is kind of meaningless unless we're saying compared to somewhere else. So think about this ball on this table in the top floor of this apartment building, okay? If I asked you how much gravitational potential energy it has, you would probably reply, well, do you mean relative to the floor? Or do you mean relative to the ground? Or even do you mean relative to the table? Right? We can easily talk about how much energy it would gain or lose by being moved. In this case, it would lose potential energy by being moved from here to the floor or by here to the ground, right? But notice both of those require us to compare it to another place, right? We can't just say it has X potential energy here until we've defined where we're saying relative to that it has that much potential energy, right? So if we call the ground 0 and we call this, let's say, I don't know, it's 100 meters high, then the table is 1 meter high, so it's at a height of 101 meters, right? All this requires, though, is we just need to first decide what is our reference point, right? So by doing this, I'm saying that it is 101 meters above the ground. So relative to the ground, the change in potential energy it would go through by moving from here to here is whatever m times g times a change in height of 101 meters is, right? But relative to the floor of the apartment, we could say it has a change in a change in potential energy of whatever m times g times 1 meter is, right? So the change in energy from here to here is obviously different than the change in energy from here to here, right? But to start thinking about them in the first place, we kind of need to define, all right, what are we comparing to? And notice, as long as we're comparing to something else, it's fine, right? No matter what, this is a change in height of 0 meters. So for example, what if we wanted to do it another way? What if we wanted to call this a height of 0 meters? Well, the table being 1 meter above that would now become 1 meter, right? And what would the ground be? Well, it's 100 meters below that, so I guess we would call this a height of negative 100 meters, right? And sometimes at this point, students will say to me, well, hang on, how can, just by changing what we called a height of 0 meters, we gave it a different amount of energy? Well, no, right? Because potential energy, we're always saying compared to where. So notice, nothing actually changes. What is the change in height to go from 101 meters to 100 meters? That's a change in height of, well, you're going down by 1 meter, right? I'll just call it a change in height of 1 meter. What's the change in height to go from 1 to 0? It's also a change in height of 1 meter, right? So we're not breaking physics or anything here. We're not saying the ball magically has a different amount of energy if it's here and we call this 0 versus if it's here and we call this 0. Right? The change in energy to move between those positions is still the same. All we're changing by doing this is changing our reference point. We are arbitrarily deciding what we're calling 0, right? And even to go from here to the ground, it's still the same as using this arbitrary height of 0, right? Because to go from 1 meter to negative 100, it's a change in height over here from 101 to 0 is a change in height of 101 meters. On this side, to go from 1 meters to negative 100, that is also a change in height of 101 meters, right? So it's still the same change in height, no matter what we're defining as our reference point of 0 meters. And so if I decide to reference the apartment floor as a height of 0, whereas you decide to reference the ground as a height of 0, okay, that's totally fine. We're still going to be consistent in terms of the physics that's going on because the change in height is still the same to go from one position to another. And therefore the associated change in energy is the same to go from one height to another, whether you use my definition of or reference point or your reference point. Okay, for example, if we were both asked to calculate the amount of kinetic energy that this ball would gain by falling to the floor, we'd get the same result. It's not like you would find that it would get more kinetic energy because it's still going through the same change in height. From an initial height of 101 to a final height of 100 is a change in height of 1 meter, right? And same for me. So the physics still is consistent either way. It's arbitrary. We choose a reference point. Okay, and then again, these are all about differences between potential energies at given points. And so what these scalar fields in terms of potential energy, what they're talking about here, right? When they say by comparing the potential energy reference to some other arbitrary 0 value at various points, all that means, to think about it with gravity at first here, right, is we pick a place to call 0. So maybe let's go with yours. We're going to say this height is 0. Okay, and then we just map out, okay, so compared to that place, what would be the change in potential energy to go from, here to here? And maybe you do the math on it and you do, G times H, and you say that per kilogram of mass it has, it would gain 10 joules of potential energy to get there, right? 10 joules per kilogram. And of course, that would be true at all of these heights here, right? And then you go up and you say, okay, there it would be 20 joules per kilogram, right? And maybe here it would be 30 joules per kilogram, okay? And that's what, do you see how this is starting to look like a field, right? We're defining every area or every location here with respect to some quantity. That quantity is how much potential energy would it gain by going from what we've arbitrarily called 0 to here, or to here, or to here. And if we could do this, if we do this for every point in space here, what we're doing is mapping out a field in terms of the change in potential energy that a mass would gain per kilogram of mass that it has by going from our arbitrary 0 line to another position. Now, using my reference point of the 0 meters being at the floor of the apartment, could I do the same thing? Definitely, right? I'm just comparing back to this point now. So maybe I would say, okay, up here at this location, maybe the associated change in energy to go from my reference point to there would be 10 joules per kilogram. And down here, it would actually be like negative 10 joules per kilogram, meaning that if we took the ball from here to here, it would actually lose 10 joules of potential energy for every kilogram of mass that it has, right? And by the time I get down here, maybe it's like negative 70 joules per kilogram. It's still a field, we're still mapping it all out, and it's still consistent with yours. Maybe this is negative 80 joules per kilogram, right? So all we're saying there is that to go from here to here, it would lose 70 joules of potential energy for every kilogram of mass that it has. And note, it's still the same thing. If we were to move something from here to here, my system says that it would lose 10 joules of potential energy per kilogram of mass that it has, right? Negative 70 to negative 80 is a change of negative 10. Your system says the same thing still. 30 joules to 20 joules is also a change of negative 10 joules per kilogram. So our systems are entirely the same in terms of the changes, which is what these are all about anyway. I just have a different reference point. I'm thinking about relative to here, you're thinking about relative to here. But the difference between any two positions within the field is still the same, no matter what our chosen arbitrary reference point is. Okay, so now that we've kind of thought about it in the gravitational field, right? We can kind of see how this is like a field in terms of changes in potential energy compared to some reference point. Let's just take it and extend it into the electric field. So how this is done in the electric field is actually the exact same idea, right? And we do, once again, we think of like a positive charge. Typically, that's what the signs imply for the changes in energy we're thinking about, right? So one person might say, okay, I'm going to define this plate as the 0, the reference point. I'm going to call that 0 volts. Okay, and then all they think about is, all right, so if I took a positive charge and I started moving it this way, right, maybe it would gain 10 joules per coulomb by going from here to here, right? 10 joules per coulomb, aka 10 volts, right? That's the same as 10 volts. We could also have called this 0 joules per coulomb. Okay, so just like up here, we were saying by going from what we're calling 0 to this height, it might gain 10 joules of potential energy for every kilogram of mass it has. Same thing here. By going from this position, a positive charge, we might say we're going to define that as where it has 0 joules. So to move to here, it would gain 10 joules of potential energy for every coulomb of charge that it has, right? And of course, that goes everywhere here. Now, to go from this definition of 0 to there, maybe it would gain 20 joules of potential energy for every coulomb of charge that it has, right? That just means 20 volts. And maybe to go from here to here, it would gain 30 joules of potential energy for every coulomb of charge that it has, right? And then finally, maybe to go all the way across the plates, to take a positive charge from here all the way to here, you would give it 40 joules of potential energy for every coulomb of charge that it has. In other words, the potential difference across the entire plates is 40 volts, right? To go from here to here, a 1 coulomb charge would gain 40 joules of potential energy if you were to take it from that position to that position. And these are all just referenced back to calling this 0, right? And again, see how this is a field, right? We're mapping out this space with respect to some quantity, giving it a numerical value, right? That quantity in this case is the change in energy it would experience for every coulomb of charge that it has by being taken from here to any position within the field. Now, it's totally possible for someone else to look at this and think, I'm not going to think about moving charges from here to somewhere else. I'm going to think about moving them from maybe here to somewhere else. That's totally fine. Maybe they're going to say, define this as their 0, right? And what they're saying there is, okay, I'm thinking about this kind of as the starting point, right? So to move it from here to here, its change in potential energy would be 0 because it's in the same spot. We just said, okay, to move it from here to here, its change would be 0. But if they do this, they're still totally fine because look, right? What would be the change in energy if they were to take a positive charge from here to here? Well, for them, it would be 10 joules per coulomb, 10 volts, right? And that's exactly the same as our change when we did it this way. We said here it would have 20 joules per coulomb. So to move it to there, it got 30 joules per coulomb. Well, that's a change of 10. theirs is also a change of 10 joules per coulomb, right? To go from here to here, that would be a change of 20 for us and also 20 for them. Right? It's still the same physics, all the same. It's not like we're going to disagree on how the physics works. We just are thinking about a different starting point for moving a charge from, and then what that associated change in potential energy would be. But the actual change in potential energy itself is still the same. It's just our starting from here reference point is different, right? Now, what would be the voltage over here? It would be negative 10, right? To go from here to here, a positive charge would lose 10 joules of potential energy for every coulomb of charge that it has. And that's fine. That's consistent with ours as well, right? Because to go from having 20 joules per coulomb to 10 joules per coulomb, yeah, that's a change of negative 10. You're losing 10 joules of potential energy for every coulomb of charge you have. And so this is a totally fine way to do it as well. You could call this, say that the voltage here is 20 volts and the voltage here is negative 20 volts, and you'll get all the same results as this one because, again, voltages are fundamentally about thinking about comparisons, right? Moving from one position to another. The only difference between our two here is we were thinking about moving from here to somewhere out here to map out the field and assign a numerical value to all the positions. They're just thinking about starting from here, but they can still think about moving it to there and what the change would be, or to there and what the change would be, and they'll get the same change as us every time, which is the important thing. And that's the idea here behind these potential energy fields. The quantity that we're mapping out in the area, which is always what a field does, is how much would something's energy change by if moved to there from some arbitrarily chosen zero reference. So with that in mind, let's take a look at this example here, okay? So we can see they've just defined this plate as their zero line. So when they map out, the changes in potential energy, the place that they're thinking of starting from, essentially, right, is here, right? What's the change to move it from here to here? 0. What's the change to move it from here to here? Well, 400 joules per coulomb. A positive charge would gain 400 joules of potential energy by being moved from here to here. Okay, now it wants us to calculate the potential difference, the voltage, at the point P. Well, notice we know that the entire voltage, the change in energy per coulomb of charge to go from here to here is 400. So what would it be to go 1/3 of the way to the other plate? Well, it's going to be 1/3 of 400, right? We know between plates are a uniform electric field. So as we go, we linearly give it more and more energy. If we only go 1/3 of the way, we give it 1/3 of the potential energy per coulomb of charge that it has that we could have if we had gone all the way. So it's just 1/3 of 400 volts or 133 volts. That's really all there is to that one. And now here's an interesting question that we've kind of just talked about, right? How would our answer to the previous question have changed if the negative plate were instead defined as negative 400 volts and the positive plate were defined as 0 volts? So if we had this situation, well, would it have changed, right? What is the change in potential energy? Because again, these are always about changes to go from here to here. It would still be an increase of 400 joules per coulomb, right? To go from negative 400 to 0 is still a change of positive 400. You're adding 400 joules of potential energy per coulomb of charge. So this just goes back to what we were talking about here, right? It is entirely arbitrary what we call 0 volts. All that means is, if we were to use this, we're kind of thinking about, all right, what would be the change in energy starting from over here? Well, a positive charge, if we brought it towards the negative plate, would lose 400 joules of potential energy for every coulomb of charge that it has, right? So we would think of this as being a change of negative 400 to go from here to here. But that would be the same change doing this, right? To go from positive 400 to 0 is also a change of negative 400. So the answer is that our answer would not change. Okay, so just summarizing there, the potential difference between the plates is still 400 volts, right? The reference value of 0 volts that is chosen is arbitrary, completely arbitrary. It's just saying, okay, we got to pick some point to reference to because we're thinking about changes, right? So it's hard to think about changes if you're not thinking about changes from what, okay? Either way, the changes stay the same. To go from here to here is a change of negative 400 joules per coulomb. To go from 400 to 0 is a change of negative 400 joules per coulomb, okay? So 1/3 of that change is still going to be 133 volts, right? To go from negative 400 to negative 367, right? That's where that would be now, is still a change of 133 volts. Okay, so next up, it asks us to draw a line to connect all positions with the same equal electrical potential as P, since that's what we're talking about at P, right? Now, there's a note there that these are called equipotential lines. Let's just first think about where would the equipotential line for this location be, okay? Well, let's imagine we're somewhere else. Vertically, we're somewhere else. So maybe we're down here. Okay, I want you to stop me when I hit the point where a charge, a positive charge, would have the same potential energy as it would at P. Ready? Here I go. I'm going to start lifting my positive charge away from the positive plate. Did I go too far? It would be here, right? That is where a positive charge would have the same potential energy as a positive charge at P. Right? To go from here to here would be the same change in energy as to go from here to P. Just like in a gravitational field, if I were to ask you, if I were holding a ball up here and there were a ball on the ground and I asked you to lift the ball until it had the same potential energy as this ball, right? Well, you'd start lifting it and you'd stop when it was at the same height. Same idea here, right? So a positive charge would experience the same change in potential energy to go from here to here as it would to go from there to there, or there to there, or there to there. So everywhere along this line, right? Just like a ball at this height, no matter where it is horizontally, would have the same potential gravitational energy. A charge at this location in this electric field would have the same electric potential energy anywhere along this line. So we actually know what that is, right? What the potential difference is there relative to this 0. We found that that would be 133 volts. So we would call that the 133 volt equipotential line. Right? If I move a charge from here to here, I am giving it 133 joules per coulomb of charge. I'm giving it 133 joules of potential energy per coulomb of charge that it has anywhere along that line. Then it asks us to draw in an equipotential line where the potential difference would be 100 volts using their definition here of 0, right? So to go from 0, 100 is a little smaller than 133. In fact, we can even do some math here and figure out, okay, all the way to the other plate would be a change in energy of 400 joules per coulomb. So 100 would be a quarter of the way, right? So about there, roughly. And all that's saying is that to move a positive charge from here to here, or here to here, or here to here, anywhere on this line, you would be giving it 100 joules of potential energy for every coulomb of charge that it has. All right, so next it answers us an interesting question. What would the equipotential lines look like around a point source? So a point source, that just means something like, a positive charge that looks like that. Not two plates where there's a uniform electric field, but one that actually has an electric field that we know decreases as you get further away, right? E equals KQ over R squared. So it decreases as we get further. What would the equipotential lines look like around something like that? Well, let's think about gravity again. It's always helpful with this electric field stuff and electric potential to refer back to gravitational fields and gravitational potential energy. Okay, so here's what we said for gravitational potential and where things would have equal amounts of gravitational potential energy, right? Like a ball here has the same gravitational potential energy as a ball anywhere along this line, right? Here's another place. If it was here or here or here or here or here, everywhere along that line, they would have the same gravitational potential energy. But what if we zoomed out more? Because ultimately the Earth really is more like this situation if we actually zoom out and think about the whole Earth. So what would these equipotential lines look like if we were to zoom out and think about the entire Earth? Well, I mean, if you're this high above the surface of the Earth, like at the North Pole, you'll have the same amount of gravitational potential energy as if you're that high above the surface of the Earth in Europe, right? Or in Africa, or in South Africa, or at the South Pole, or in Australia, right? As you go all the way around, anytime you're an equal amount of height above the surface of the Earth, you're going to have an equal amount of gravitational potential energy. So the equipotential lines in terms of gravitational potential energy would look something like that around the Earth, right? A ball would have the same gravitational potential energy here as it would here, or here, or here, or here. Right? So there are some equipotential lines around the Earth in terms of gravitational potential energy, right? Everywhere on this line or circle, it would have the same gravitational potential energy. Out here, it would have more gravitational potential energy, but then all the way around in the circle, all of those points would have the same amount of gravitational potential energy. Move out further, same idea, right? Increase the gravitational potential energy, but then all of these would have that same amount. So let's take that now and think about electric potential energy. Okay, so yes, right, as we move away from this charge, we will be changing the amount of potential energy, electric potential energy that we would have there, right? That another charge would have if placed there. But everywhere, so if I move further away, right, in this direction versus in this direction the same distance, or in this direction the same distance, right, at all of these locations that I'm drawing out right now, you would have the same change in potential energy to go from here to here, right? Or from here to here. The same way on the Earth, a ball would be given the same amount of potential energy to be moved from the surface to here, or from the surface to here, okay? And so you could imagine the equipotential lines around a point source would look something like this. And obviously we could draw like infinitely many of these, right? But just putting in a few of them, right? A charge would have the same amount of potential energy anywhere around this point source of the electric field. So this simulation actually comes with a tool that lets you draw equipotential lines, right? So as I touch that little pencil button there, all it's doing is drawing in all the locations that would have the same change in potential energy as the location that I'm currently at, right? So like all of these would have the same potential energy relative to this charge, right? Notice it makes this kind of circular shape. Can even get some more complicated looking equipotential lines when we have more charges involved and therefore the electric field isn't quite so simple, right? But again, all it's showing is that everywhere along this line, a charge would have the same amount of potential energy. Everywhere along this line, a charge would have the same amount of potential energy. Cool, right? All right, let's take a look at this one now, okay? They've chosen kind of a, honestly, weird way to define them, but we know that that doesn't really matter, right? What we define as our zero reference point is entirely up to us, because this is all about the difference in potential energy between positions. So it asks us here to draw in the plus 200 volt equipotential line, right? Based on the system that they've defined here. So it's been labeled this way for us, right? And we're just trying to figure out, okay, using this reference system, where would the 200 volt line be? So let's just think about this a bit. We're got to go all the way across the plates. What's the voltage across the entire plates? What is the change in potential energy per coulomb of charge if you were to go all the way from here to here? Well, it's 1200 volts, right? 500 to get to 0, and then another 700 to get to plus 700. So based on that, right, if we were to split this up into 12 even slices, essentially, right, we could count out where the plus 200 volt equipotential line would be. So there, I kind of eyeballed it to split it in half first, right? We have a 1200 volt potential difference across the plates. So halfway would be about a 600. So negative 500 plus 600. That should put us at about plus 100. And then you can think of it, just splitting it up. Okay, so halfway from 100 to 700 would be 400. So 200 would be about a third of the way to that. Just kind of eyeballing it here. You could break out the ruler and actually measure, but I'd say that's a pretty reasonable estimate there, right? And again, all that's saying, again, is if you were to go from this plate to that position, what would your change in potential energy per coulomb of charge be? Careful, it wouldn't be 200 joules per coulomb, right? We would be 700 joules per coulomb. So if you had called this 0 volts, which might have made more sense, then this would be plus 600 and this would be plus 700. But notice it's still entirely consistent, right? To go from negative 500 to 200 is a change of plus 700. To go from 0 volts to plus 700 is a change of plus 700. It's all about changes here referenced to some point. Then it asks us to draw the electric field vectors in between the two plates. Okay, so we got to ask ourselves, right? What would be the direction of the electric field in here? Do you remember how we always define the direction of the electric field? It's in the same direction that a positive test charge would feel a force. So if I put a positive test charge into this field, which way would it feel a force? Well, it would be repelled by the positives to the left. It would also be attracted by the negatives to the left, right? Like repel, opposites attract. So the electric field would be drawn this direction, right? From the positive to the negative plate. So something like that. My lines aren't very straight, but hopefully you get the idea there. Okay, and we know because they're charged parallel plates, this field is uniform as well. So it's got the same strength everywhere. Okay, now again, that field's there no matter what. Whether or not there's something in there feeling a force, just by the nature of this having charge and this having charge, there is an electric field here that could exert a force on a charged particle if it were to enter this field. Which brings us to C, which asks us to draw the force vector on a singly ionized atom. Now, do you remember what that's assumed to mean in physics if something has been ionized? It always means, and we'll go over this more in Unit D, okay, why that's the assumption in physics when we hear the word ionized, but it always means that an electron has been removed from the object, okay, or from the atom. Right? So singly ionized just means it's single. One electron has been removed. That's what singly ionized means. Okay, so in physics, typically, unless it's explicitly stated that it's an ion that has gained electrons, to say something has been ionized means it has lost an electron. Now that brings up the question, if it's lost one electron, what's its charge? Positive or negative? Well, electrons are negative, right? We know that. So if it's lost a negative electron, its charge would be positive, right? It was a neutral atom, but it's now got one more protons than it does electrons, so overall its charge would be positive. So we've got some positive charge that's in our electric field. And so the question is just then, what would be the force acting on this positive ion in this electric field? Well, I mean, there's two ways we could think about it. We know the electric field is in this direction, and the electric field is defined as the direction in which a positive test charge would feel a force. So a positive test charge should feel a force in the same direction as the electric field, right? So also from right to left, or towards the left side of the page, we could say, right? The other way to think about it is just ask yourself, well, this is positive, like repel. This is negative, opposites attract, so it should feel a force to the left, okay? What about a negative ion? Which direction would it feel a force? And again, two ways we could think about that, right? We know that the electric field is defined as the direction a positive test charge would feel a force, and therefore a negative test charge would feel a force in the opposite direction, right? But we could also think about, in fact, the fact that, like repel, and opposites attract. So the negative would be pushed this way, okay? Now, again, you might not always be able to rely on both of those, right? Sometimes you're just given the electric field and asked which way the force would be, and you're not shown what the charge on these objects are, right? And for that, you'd have to rely on the definition of the electric field. So if I told you the electric field looked like that, and there was a, let's say, negative charge in there, which way would it feel a force? It would feel a force in the opposite direction as the electric field, right? Because the electric field is defined as the direction a positive test charge would feel a force, and negatives would feel forces in the opposite direction as a positive. Anyway, moving on here to this one, it asks us, using the words parallel or perpendicular, compare the direction of the equipotential lines to the electric field vector. Well, look at this. The electric field lines are in this axis. The equipotential lines are in this axis. So are they parallel or perpendicular? They're perpendicular. And that actually makes a ton of sense when we think about it. It's not just like a special coincidence for this one or anything like that, that's at a 90-degree angle, right? Because how do you change something's potential energy in this field? Well, you have to either move it with the electric field or in the opposite direction as the electric field, right? But moving it perpendicular to the electric field is never going to change its potential energy, right? And that's why you would find equipotential lines by moving along a line that is perpendicular to that electric field, right? If you're not moving parallel or anti-parallel to the electric field, you're just moving perpendicular, well, you're not changing its energy. And that expands even out to this situation, right? Look at this. What would the gravitational field lines look like around the Earth? Well, we know the gravitational field always pulls objects towards Earth's center. Now, once again, what do you notice about the direction of the gravitational field lines that I'm drawing in now and the equipotential lines that we drew in earlier? They are perpendicular. Right? And again, that makes sense because if you move against the gravitational field, you're giving it more potential energy. So moving this way, it can't have equal potential, right? Moving this way, it can't have equal potential. Only moving it perpendicular to those field lines can it keep the same gravitational potential energy. What would the electric field look like around this charge? Well, it would look like this, right? Once again, perpendicular. We know that the electric field gets weaker as we move further away, right? And we know the amount of potential energy changes as we move further away. The only way to keep the same amount of potential energy is to stay the same distance away and therefore move perpendicular to the way the field lines are pointed. Cool, right? Even in these more like complicated situations where we have multiple charges, watch, those are the equipotential lines. I'm going to add into this simulation now the electric field arrows. And look at that. Pick any place, right? Pick any place where there's an equipotential line and look at the electric field vector that's around it. They're always perpendicular to each other, right? Perpendicular there, perpendicular here, perpendicular here. Okay, so again, it makes sense. You only change the potential energy by moving with or against the electric field. So if you're moving perpendicular to the electric field, your potential energy stays the same. In other words, you're moving along an equipotential line by moving perpendicular to that electric field. All right, next up it asks us about the direction of the equipotential lines to the force vector. Well, unsurprisingly, those are also perpendicular, right? 90-degree angle. Well, again, that makes sense because if the equipotential lines are perpendicular to the electric field, the force vector is always in the same axis as the electric field. It might be in the same direction as the electric field for a positive test charge, or in the opposite direction as the electric field for a negative test charge. But either way, it's still in the same axis. So if the equipotential lines are parallel to the field, they're going to be perpendicular to the field, they're going to be perpendicular to the force vector as well. Right? And we kind of answered this one in the process of answering that one. The electric field vector compared to the force vector, well, yeah, that's going to be parallel, right? The electric field is defined as the direction in which a positive test charge would feel a force. So inherent in that definition is that a force vector for a positive test charge is in the same direction as the electric field. Can't be in the same direction without being parallel. And even for a negative test charge, they're still in the same axis. You could say, if you wanted to, you could say it's anti-parallel. Anti-parallel just means like that, right? This would be parallel, and that would be anti-parallel. So parallel versus anti-parallel, but really anti-parallel is kind of just being a more specific way of saying parallel. They're in the same axis, right? They're just in opposite directions. So this is true even for a negative test charge. Might feel a force in the opposite direction as the electric field, but it's definitely not perpendicular, right? It's still parallel, right? If we had something like that, if we were in an electric field to the left side of the page, a positive would feel a force to the left side of the page, a negative would feel an electric force to the right side of the page because of that same field, but both are in the same axis still. This is parallel to this. More specifically, anti-parallel, but same idea. All right, so the next thing we're going to talk about here is Millikan's oil drop experiment. One of the most famous experiments in physics, history. Also one of the most hated physics labs by university students all over the world. You'll do it in some of your first year university physics courses if you plan on taking those. It's not fun to do. I mean, it's really cool, don't get me wrong. It's very fun to do and to be walking through the same steps as Millikan and finding this. It feels really cool to do it. However, the lab itself is famously kind of tedious and difficult because you have to watch these oil drops very carefully and you have to watch them go up and down like 10 times and you always lose them on the 9th time and then you have to start over. It is a really cool lab and it's fun to do in that regard, but it's famously not very well liked by physics students when they have to first do it in university. I can speak from experience there. But anyway, what is this experiment? Well, remember, I've mentioned this before, that we will talk about how did we actually figure out the elementary charge, E, right? You know it as the charge of an electron, if negative, or the charge of a proton when positive, We've been taking that number for granted, but we haven't actually talked about how did we figure this out. It's not like you can, hold an electron in your hand and test it out, right? Well, the answer is this. It's Millikan's oil drop experiment. This is how we first determined the charge of a single electron, and therefore the elementary charge. So it was done by an experimental physicist named Robert Millikan. This is not the last you will hear of Robert Millikan in Physics 30. Millikan is an experimental physicist, which is, a very important role. Sometimes the theoretical physicists get a little more, clout, like the Newtons and the Einsteins of the world, right? They come up with these theories and these hypotheses on how the universe works, and that's great, right? Obviously, that's good to have hypotheses and theories, but they really don't mean much until they are tested, until we can come up with an experiment to see, okay, is this actually a good model for how the universe works? Can it explain how the universe works, right? And that's how science moves forwards. We come up with hypotheses, we test the hypotheses, and we're actually trying to disprove it. And if we fail to disprove it, we become a little more confident in that hypothesis and the theory associated with it being a valid representation of how the universe works. So very, very important to have experimental physicists like Robert Millikan, and he was very good at this. He dedicated his life to testing the hypotheses and the theories of theoretical physicists, and he ended up supporting or even refuting a lot of them in his lifetime. And this is probably his most famous experiment, the Millikan oil drop experiment. Like I said, this is how we figured out the charge of an electron for the first time. So how it basically works is that you take some very fine drops of oil, and the oil drops have a known mass. Essentially what you do is you spray them in a very fine mist, picture like a perfume mist almost, right? Very fine droplets of oil, and they come down here, Okay, you might be wondering, how the heck would you know the mass of those oil drops? Well, you look through it, you look into this field through this little microscope here, and on that is a little ruler. So with the ruler and the oil drops behind it, you can kind of use it to measure their radius. Since they're spherical, you can figure out its volume, and the density of the oil was known very well. So if you know the density of something and you know its volume, you can figure out its mass, okay? So you know the mass of these oil droplets, which means you know the force of gravity they feel, right? Because this experiment was done on Earth, and so the force of gravity we know is just mass times acceleration due to gravity, right? So if you know something's mass, you know the force of gravity it's feeling. Now, this is not just a box. Notice these are two charged plates, and the plates, the voltage across the plates, and therefore like the strength of the electric field between them, was adjustable. So you could adjust the voltage and the strength of the electric field in between them, changing the electric force that was acting on these charged drops. Okay, so we took these oil drops, gave them a charge, and then Millikan messed around with the voltage across the plates, adjusting the electric field between the plates. Okay, and if you're changing the electric field, you're changing the force that's on the oil drops, the electric force, right? And so what he would do is he would charge this plate to repel whatever charge was put on the drops. He actually gave them a negative charge. He did this using X-rays. Basically, we'll talk about this, how the X-rays work and how they work to ionize air molecules and atoms in Unit D. But short version is X-rays can knock electrons out of molecules in the air, and then the oil would pick up those extra electrons. That's how he got the oil drops to be charged, okay? The details of that aren't super important to understanding generally how the experiment works, but, you know, never hurts to know more, okay? So the oil drops are charged, and he set up this plate to repel them. He made this plate be negatively charged, and the oil drops are negatively charged. So think about that. If we know that the force of gravity is pulling the oil droplets down, and that's easy to calculate, right? We can easily calculate the force of gravity, and the electric force is going to be pushing them up. Now, if we can perfectly balance those forces, we know that the electric force acting on the oil drop is the exact same as the force of gravity acting on it downwards. And again, we can calculate what that force is. So we could calculate the electric force acting on it upwards. And I'll leave it there for now. We'll talk about how this leads to actually figuring out the charge, okay? But let's just remind ourselves of what's going on here, okay? Because what Millikan did is get the oil drops so that they were suspended, essentially floating. Now, that's a little bit simpler than the actual experiment, but that's the core idea of it, right? Try to get it so that the forces acting on it are balanced so that it's not moving at all, okay? Just reminding ourselves of how this works, the physics involved here, the dynamics, okay? It wants us to draw free body diagrams for drops that are, first up, suspended. So remember, a free body diagram just takes some object that forces are acting on and simplifies it down to a point. So we can really just focus in on the forces. Okay, now remember, do forces make objects move? Not quite. Forces make objects, or at least unbalanced forces, make objects change how they're moving, right? A net force doesn't necessarily make an object move. It makes it accelerate, okay? So if it's suspended, it's not moving at all, and it's not accelerating, right? The forces are definitely balanced. So the force of gravity, which is just mg, downward, must be just as large as the electric force upwards, like that. Now, again, what is that electric force? Do we have an equation for it? Well, we do have this one, right? That the force acting on a charge in an electric field will just be Q times that electric field, right? Now again, Millikan didn't necessarily directly measure the electric field, but he did know the voltage, and that was easily measured and easily adjusted. So the voltage, if he knew that, and the distance across the plates, well, that's very easily measured. You could do that with a ruler. So he essentially did have the electric field, right? So this, you can start to connect the dots here, right? With the voltage and the distance across the plates, you know the electric field. If you know the electric field and you can figure out the electric force because it's balanced with the gravitational force, and you can easily calculate the gravitational force because it's just the mass times acceleration due to gravity, you can start to figure out what charge is actually on those oil droplets. Okay, for now, let's just leave it here. The electric force is going to be Q times the electric field, right? Which makes sense. The electric field is, again, how many newtons something will feel for every coulomb of charge that it has. So multiply it by how much charge it has, and you get the actual force. All right, next one, moving up at 3 meters per second. Be very careful. Most common student mistake here is to say Fg equals mg, and they say, okay, it's moving up, so the force up must be bigger. Now, would that be moving upwards at a constant speed of 3 meters per second? Nope, right? This would be accelerating upwards. It would be getting faster and faster and faster. It wouldn't be moving up at a constant speed, right? We know that from physics 20. If it's moving up at a constant speed, that is uniform motion. The forces are still balanced, right? It is uniform motion. Net force is 0. So just as hard up as down, right? Newton's first law. If the acceleration is 0, the net force must be 0, right? An object at rest or in uniform motion must have no net force acting on it. Okay, now here we go. Accelerating up. So the acceleration is not 0. That means the net force is not 0. So if it's accelerating upwards, the electric force in this case must actually be larger than the force of gravity downwards. That's how something accelerates upwards. There needs to be a net force up, right? So like this much of each force cancels each other out, but we're still left with an overall upward net force. All right, now accelerating down at 3 meters per second squared. Pop quiz, are the forces balanced or unbalanced? Unbalanced, it's accelerating. Its velocity is changing, right? Now, a common student mistake here would be to draw Fg much bigger, but does that make sense? Did the oil droplet's mass change? No, right? It should still be feeling the same force of gravity as we've been drawing. So how do we get a net force down then, if the force of gravity is still just as large downwards? Well, the upwards force, the electric force, must just be smaller, right? And that makes sense in the context of the experiment as well, because we can adjust the voltage across the plates and therefore decrease the electric field if we need to. All right, here's an interesting one. Accelerating down at 9.81 meters per second squared. So it's accelerating, the forces are not balanced, but this is a very specific number, right? If you're accelerating at 9.81 meters per second squared, you're in free fall, right? You're just accelerating at acceleration due to gravity. So that all that means to be in free fall just means the only force acting on you is the force of gravity. So this would be the case if you turned off the electric field altogether. Maybe you disconnect it from the battery or just turn the power off, right? And then the oil droplet would be in free fall. Now, what about this one? Accelerating down at 12 meters per second squared. So how would you accelerate down even faster than the force of gravity would pull you? Well, another force must also be pulling you down, so that the net force downwards is even larger than your force of gravity, and therefore your acceleration is even larger than the acceleration due to gravity would be. So this would be the case if we were to, say, reverse the polarity of the charge on the plate, right? So the plate, the drops are negative, and we actually switch it so this plate is negative. So not only is gravity pulling them down, the electric field is also pulling them down, right? We need to have two downward forces to get an acceleration due to gravity an acceleration downward that's even larger than our free fall acceleration from just the force of gravity. So just to give a visual here is a setup of the Millikan oil drop experiment, okay? So notice I can adjust the voltage, and therefore you can see as we have a higher voltage, we have a stronger electric field. That checks out with the equation, right? We know that the electric field is equal to the potential difference, or the voltage, divided by the distance between the two positions. So look at that equation. Larger voltage in the numerator means larger electric field as an answer. So it makes sense that increasing the voltage gives us a stronger electric field. And then if you look at the equation right above it, we can see that a stronger electric field also corresponds to a larger electric force. Makes sense. Going back to this now, let's just run it with no electric field, just so you can see, right? And the oil droplet is in free fall. It just falls down. The only force acting on it is the force of gravity. Okay, let me bring it back though. And now let's actually apply voltage across the plates. And essentially, here is what Millikan's trying to do, right? He's trying to get it so that the electric force upwards is the same size as the force of gravity downwards, so that the oil drop is not accelerating. Now, technically you can have it moving and just not be accelerating. The easiest way to know for sure the forces are balanced is if you could get it to just sit completely still, right? And it's kind of tough to do, right? But you can kind of see the idea here. Stronger electric field, the force is too big upwards, it's accelerating upwards. Lower electric field, the upwards electric force is too weak, it's accelerating downwards, right? We're trying to perfectly balance those because, again, when they're perfectly balanced, we know the force of gravity is the same as the electric force. And if we know those are the same and we can calculate the force of gravity, then we have the electric force as well. And if we know the electric force and we know the electric field strength, we can get the charge. And we're starting to walk down the same steps Millikan did to figure out how can we find the charge of an electron. Okay, so let's start putting these ideas together now and actually follow in the footsteps of Millikan here. Okay, so it wants us to derive the equation that would be used to determine the charge on the drop if the drop was suspended. Okay, now what did suspended mean again? It meant the force upward on it was just as much as the force downward, right? If it's suspended and it's just floating there, obviously the forces are balanced. Otherwise, it would be accelerating. Okay, and so since the two forces are the force of gravity pulling it down and the electric force pushing it up, they have to be equal when it's suspended. All right, now remember, all Millikan knew from his experimental setup was the voltage, could adjust that and read it with a voltmeter. The plate separation, that's easy to do, just take out a ruler and measure how far apart they are, okay? And the mass of the oil drop. And therefore, those should be all that appear in our equation, right? We can only calculate with numbers that we know. So let's think about this, right? What do we know? We know that if the drop is suspended, F net equals 0, right? That's just Newton's first law. So right off the bat, it's asking us, which physics principle did we use? Well, from the back of our formula sheet, the physics idea that we are relying on to make this calculation and analyze this situation is actually just uniform motion, right? The net force being 0, the forces acting on an object being balanced, means that it will not accelerate. That is the idea we're relying on here, okay? Sometimes students have a tendency, they say, well, it's talking about charges, so I guess we're using the law of conservation of charge, maybe, right? But think about it. Are we applying that here? Do we need to use the fact that charge is not created or destroyed? Is that the principle guiding our calculation here, right? Guiding our analysis? Not really. The underlying principle here that we're relying on is the fact that if the forces are balanced, these two must be, if it's not accelerating, the forces must be balanced and these two must be equal, right? When students ask me, how do I know which physics principle I'm using? Because they're all true, right? And that's true. They are all physics principles. They are all valid and true. It's not like any of them are ever false for a given question. But ask yourself, which one guided your thought process? Which one did you actually have to rely on to be able to start making your calculations and do your analysis, right? That is the physics principle you're relying on in that situation. All right, so F net equals 0, but F net, as always, is just the result of adding up all the forces acting on the object, right? So F net here is just the electric force plus the force of gravity. So that equals 0. and therefore the electric force acting on it is equal but opposite to the force of gravity. Just like we said, right? That was kind of our logic from the beginning. So here the physics is speaking to us through the math again. However hard the force of gravity is pulling it down, the electric force must be pulling it up, right? So pulling it just as hard, but in the opposite direction. Okay, now great, but Millikan didn't directly know the electric force, and he didn't directly know the force of gravity. Those had to be calculated from quantities that he could measure. So we're not done here. We got to keep breaking this equation down a bit further, right? So we've got a choice here, and we kind of already talked about it a little bit, but there are two equations for the electric force on your formula sheet. There's this one, right? Fe equals the charge times the electric field strength, or there's Coulomb's law, KQQ over R squared. So we do have a choice to make. Which one of those makes more sense for this situation, right? We've got charged plates. Do we know the charge on the plates, right? Do we know like how far we are from a source? Is this a field that's, changing as we get further and further away? It's a uniform electric field. It's the same everywhere, right, between charged parallel plates. We don't know the charges on these plates, okay? So this one definitely does not make sense, right? What we do know is the voltage, and we can measure the distance across the plates, which means we can figure out, as we said, the electric field. So I would say makes a lot more sense to write our force in terms of the electric field, because that seems like something we can calculate. So Q times the electric field strength is equal to force of gravity, but we know that's just mass times acceleration due to gravity, or mass times gravitational field strength. Now we're getting there. We're supposed to determine the charge on the drop, so obviously we want the charge in our equation, because that's what we're trying to find. We know the mass. We can measure the mass of the drop, so that's good. That can appear in our equation. And since this is happening on Earth, we know the gravitational field strength. It's just 9.81 newtons per kilogram, okay? Problem is, we didn't directly measure the electric field. So, do we give up, or do we think about a way we could write the electric field in terms of things we do know, right? So this, right, we could say, but electric field is just the potential difference, or the voltage, over the distance between the two positions you're thinking about. So if we think about the voltage across the entire plates and the distance between them, that's probably the easiest way to do it. We basically have the electric field. And there we go. We knew the separation distance between the plates, and we knew the voltage. So if we replace the electric field in our equation here with this, which it's equivalent to, everything in our equation will be in terms of things that we knew, or that Millikan could measure. So that means this could become Q times the electric field strength, yes, but the electric field strength is just the voltage over the separation distance. So voltage over distance, right? Q times the electric, Q, oh my goodness, Q times the electric field strength, right? This is the electric field strength, same equation still, equals negative mg. So all that's left to do is solve for Q. So let's go ahead and multiply both sides by d because we're dividing by it, and then divide both sides by v because we're multiplying by it. And doing that, I got this. Okay, this, I find, it's almost one of those moments that like gives you shivers, right? It just feels so cool to be walking through these same, kind of footsteps that led to finding this fundamental value of how the universe is put together, right? This equation, it's cool to think about. It gives you pause to think how neat this is, that we've just come up with just this fairly simple apparatus, some drops of oil, some charged plates, right, and a microscope. We can actually work out the charge of an electron. Now, you're probably saying to me, wait, this would not find the charge of one electron. How would you know the charge of one electron? Because all you're finding is the overall charge of an oil drop, right? And who knows how many electrons the oil drop gained or lost. It's not like you can see the electrons. It could have lost 100 electrons or 20 electrons or 1 electron or anything in between, right? So how did this actually give us the charge of the electron? Good question. That's a very good question. How it worked was Millikan did this, and he did it over and over and over again. Like any good experiment, you do as many trials as you can. He did it for tons and tons and tons of oil drops. And he used it, and he calculated the charge over and over. And the resulting data that he got from calculating the charges on all these oil drops looked something like this. Like he might have seen charges of, 3.2 times 10 to the negative 19 coulombs. And sometimes he saw 4.8 times 10 to the negative 19 coulombs. And a lot of them had charges like 6.4 times 10 to the negative 19 coulombs. Or, 8.0 or 9.6. And sometimes, yes, even ones had 1.6 times 10 to the negative 19 coulombs. Okay? But what he never, ever, ever saw was anything like 0.8 times 10 to the negative 19 coulombs, or 1.5 times 10 to the negative 19 coulombs, or 2.4 times 10 to the negative 19 coulombs. He never saw anything like that, okay? Or, again, something in between numbers like this. He never saw 5.6 times 10 to the negative 19 coulombs. Nothing like that ever came up, and he did this for many, many, many oil drops. And so think about that. What would you start to reason if everything you saw was a number like this? Do you notice what all these numbers kind of have in common? They are all multiples of 1.6 times 10 to the negative 19 coulombs. So think about the implication there, right? You've done this thousands of times for lots of different oil drops, and no matter what, everything is always a multiple of 1.6 times 10 to the negative 19 coulombs. And what's more, the lowest amount of charge you've ever calculated from doing this experiment was 1.6 times 10 to the negative 19 coulombs. It was never anything any lower, right? And so what Millikan said was, he reasoned out, right, well, this must be the charge then of one electron, because you can lose or gain one electron, you can gain 2 electrons or 3 electrons or 4 or 5 or 6 or 100, but you can never gain half of an electron or 1.5 electrons or 3.5 electrons, right? Or 3.2 or any non-integer number. So he noticed that the charge was always a multiple of this number that you know and love, the elementary charge. And so he reasoned out correctly, as we've later, proven with more precision, that this was the charge of a single electron and the smallest possible amount of charge. And again, it's the smallest possible amount because there's no such thing as half of an electron. You can have an electron, you can have 2 electrons, you can have 0 electrons, but there's no such thing as half of an electron. It's what we call an elementary particle. It is a fundamental building block of the universe, and you can't break it down any further than that. Right? Just as an analogy for the reasoning here, it's like you have a mystery bag full of coins, and you're not allowed to look at the coins, but you're allowed to take them out, put them in, take them out, take as many out as you want, put as many in as you want, and then all you can ever know is the value of the coins that are in the bag, right? And you do this over and over again, and sometimes it's worth 25 cents, and sometimes it's worth 10 cents, and sometimes it's worth 5 cents, and sometimes it's worth 60 cents, and sometimes it's worth $1, right? And all of the coins are the same, okay? But you're trying to figure out what's the value of one coin, right? And if you do this enough, you start to notice, okay, well, the lowest I've ever seen is 5 cents, right? And everything is always a multiple of 5, so this must be a bag full of 5-cent coins. That's kind of the idea here, right? Do it over and over again, and eventually you find that no matter what, it's always a multiple of this. By the way, this idea here that it was the smallest possible amount of charge, that's an idea known as the quantization of charge. Now, quantization is something you will become very familiar with by the end of Physics 30, and all it means is that there's some minimum amount. You can make up bigger amounts with multiples of it, but it's the smallest possible amount and you can't break it down any further. For example, a population is quantized into individual people. You can have 1 billion people, you can have 10 people, you can have 1 person, but it's quantized to that 1 person because there's no such thing as half a person. an idea known as quantization of charge. There's a minimum amount of charge. All other charges are made of multiples of this. All right, now the last thing we're going to look at in this lesson, and therefore in chapter 11, is, again, not really anything new in terms of ideas, but just a new situation to analyze, I suppose, which is how do these electric fields and the forces acting on them on charges because of the electric fields, how can we actually analyze how that will affect the motion of the charge? Okay, so we've got here an electron that's traveling horizontally, and it enters the region between two charged parallel plates at the vertical midpoint as shown below. We want to calculate the minimum speed the electron must have in order to clear the 2 centimeter long parallel plates if the potential difference between them is 2000 volts. All right, well, let's not, get overwhelmed here. Let's just break this down and think about what's happening. So the electron was just moving sideways. It was traveling horizontally, but then its path changed to go like this. Now, why did that happen? Why did its path change? Well, it's an electron and it entered an electric field. It has charge. Anything that's with charge in an electric field will feel a force as a result of that field, right? And this checks out. They're showing us that the electric field is towards the bottom of the page. Electric field is defined as how a positive test charge would feel a force. So since an electron is negative, it felt a force that caused its path to bend this way, upwards, towards the top of the page. Now, at any given moment, what direction would that force be on the electron, right? Whenever it's in here, common student mistake is to say, oh, well, it bent like this, so it must have, the force must have been pushing it like that. But would that? Don't forget everything we know about electric fields, right? Think about what we just said. What kind of force would an electron feel in these plates? Well, the electric field is down. It's just feeling a force upwards, right? There is a force acting on it upwards. There's no force acting on it sideways in the x-axis, right? There's only this vertical electric force pushing it up towards the top plate. Okay, and so its motion changes like we would expect. If something's experiencing a force upwards, its velocity would change. It would accelerate. Which way? It would accelerate upwards. Now, question for you. Does that upwards force, that y-axis force, have any effect on the sideways velocity? If something's moving sideways and we push it up, does that change how fast it was moving sideways, right? Are you getting flashbacks to Physics 20? You might be. That'd be a good thing if you were. Do you remember when we did projectile motion in Physics 20? We would take maybe a ball and throw it off of a cliff with some horizontal velocity, right? Now, is there any force acting on the ball sideways to make it go faster this way or slower this way? Is there any X force once it's left our hand and it's flying through the air? No, right? There's only a y-axis force of gravity, and there's only a y-axis acceleration. So whatever initial velocity it had in the x-axis, it keeps the whole time, right? Its vertical velocity changes for sure, but there's no force acting on it horizontally, so there's no horizontal acceleration, and so its initial velocity in the x-axis is the same the entire time, right? What the ball does do is get faster and faster downwards because of acceleration due to gravity. Something like that, right? Initially, it wasn't moving downwards because we threw it sideways, but the force of gravity accelerates it downwards, so its downwards velocity gets larger and larger and larger. But there's no force pushing it to the right or to the left, so there's no acceleration to the right or to the left, and therefore there's no change in its x velocity, right? It always has that same sideways velocity. It's just getting faster and faster downward. Do you see how that's the exact same thing that would happen here, right? Is there any force acting on this electron sideways to change its horizontal velocity? No, right? So, thinking through this a little bit, just kind of starting to make a bit of a game plan, we know that the electron is going to be accelerating vertically. we know that it's not going to be accelerating horizontally. And we know that those two motions are completely independent of each other, just like they were in physics 20, okay? When we did projectile motion then. So do you remember, it's a good strategy to kind of separate them out. We do just essentially have two kinematics problems happening at the same time, right? We've got a horizontal motion situation and a vertical motion situation, an X and a Y kinematics problem. They're just both happening simultaneously, right? This travels some distance and it's moving at some velocity horizontally. It also vertically starts out from a velocity of 0, reaches some final velocity, and has some acceleration. And we can think about that acceleration because we know the mass of an electron, right? We always have that. And we can kind of start thinking about the force that's acting on it because we do have the voltage and we do have the distance, so we could maybe figure out the electric field. But let's not get too ahead of ourselves. This is a projectile motion problem. It's just that it's not a ball being thrown off of a cliff. It's an electron passing through an electric field, right? A ball being thrown sideways in a gravitational field is fundamentally no different than an electron moving sideways in an electric field, right? The same ideas are going on here in terms of the kinematics and the dynamics. It's just a different force that's causing it all, the electric force instead of the gravitational force. So in the x-axis, let's just break down what we know. In the x-axis, it's not accelerating. The net force in the x-axis is 0. So we actually have uniform motion, right? Do we need to think about VI, VF in the x-axis, the initial velocity, the final velocity, or the acceleration in the x-axis? I mean, we could, but the initial x velocity is the same as the final x velocity because the acceleration in the x-axis is 0. Right? Because the net force in the x-axis is 0. So in the x-axis, we can actually just get away with v equals d over t, because that is what's happening, right? Horizontally, it is just covering the same displacement each second. Okay, it's got uniform motion in the x-axis. So what do we know? We know it needs to travel 2 centimeters to clear the plates, right? It's asking us what's the minimum speed it could be moving to clear the plates. Because what is going to happen here is the electron is going to be pulled up to this plate and crash into it eventually, right? The only way to avoid that is to be going fast enough that by the time it accelerates vertically to this plate, horizontally, it's already traveled the 2 centimeters it needs to have cleared them. So our dx, the horizontal distance it needs to travel, is just, whoops, that's too many zeros, 2 centimeters, or 0.02 meters. Now its x velocity, its horizontal velocity, well, that's what we're actually trying to figure out, right? How fast did it need to be going so that it had traveled those 2 centimeters before the electric force could bring it crashing into that plate? So that is what we want to know. Put a little question mark there. I'll put a star next to the question mark too, just because often there's a couple things we don't know. Star is just to indicate we don't know it, and that's what we got to figure out. Now the time, like I said, right, there we go. There's a perfect example. We don't know the time, okay? However, like you might remember from physics 20, often the time is the key to solving these problems. Because again, the x and the y-axis motions are completely separate from each other, right? This vertical force has no effect on how fast it's moving sideways. It's not in the same axis, right? It's not pushing it to the left or the right. So it maintains its x velocity. However, it's doing both of these things. It's moving vertically this far and horizontally this far in the same amount of time. It's not like the electron split into 2 separate entities and somehow took a different amount of time to move from here to here than it did to move from here to here, right? Going back to physics 20, remember this, right? If we give it a sideways velocity initially, all those dots are doing are tracking its motion vertically and horizontally, right? And so vertically, yes, we have non-uniform motion. Horizontally, we have uniform motion where it's always covering the same distance each second. It's just doing both of them at the same time. with the ball being thrown sideways off the cliff, we separated it into its X and Y situation, and we knew that horizontally it had traveled this far, vertically it had traveled that far, right? But the key that linked the two was that it took the same amount of time to do them. Yes, it did go from here to here sideways, and yes, it did go from here to here vertically. It just did both of those things at the same time by going like this. So while we don't know what t is, what the time is in the x-axis, we know it's the same as the time we would calculate in the y-axis if we could calculate it in the y-axis, right? Now, notice in the x-axis, we don't know very much. All we know is how far it had to go, right? If I asked you, if I said, hey, I walked 20 meters, how fast was I going? Your response would be, well, how long did it take you, right? So same idea. The x-axis right now, we do not have enough information. But maybe in the y-axis, we'll be able to find the time. If we can find the time it would take for the electron to move vertically from here to here, well then, hey, whatever time it took to do that is going to be, for this situation, the same time it took to do this horizontally. Now in the y-axis, can we say v equals d over t in the y-axis? No, right? Because there's not just one v. Initially, how fast is it moving vertically? Not at all, right? It was moving horizontally, so its y component of its initial velocity was 0. Over time, that grew, just like we drew with the ball as it got faster and faster in the y-axis as time went on, right? But it doesn't just have a v, it has many different v's. Starting from 0, it increases up to some maximum downward velocity. So we can't just use uniform motion v equals d over t, right? We've got to think about this in terms of accelerated motion and all of our kinematics variables. So there's displacement, there's the initial velocity, the final velocity, its acceleration, and the time in the y-axis, d, vi, vf, a, and t. Now, once again, we don't know what the time is in the y-axis, but we know it's the same as whatever the time is in the x-axis. Okay, so let's just go through our variables now and see what we know and what we don't know. Again, just because we don't know it doesn't necessarily mean we need it, but we'll see. So the vertical displacement that it travels through, do we know that? Well, yeah, right? It's going to have to go this far before it crashes into the plate, right? So we want to know if it has to go that far to crash into the plate, right? How fast does it need to be moving sideways so that sideways it's already cleared the plate by the time it does that, by the time it moves from here to here. So just to visualize here a bit what I mean by that, right? If we send a charged particle in, I know this is a different situation because it's a positive, but same general idea, right? That wasn't going fast enough. So the vertical acceleration already brought it to the top plate and it's crashed into it before it could move far enough horizontally to clear the plates, okay? So if we make it go faster, it'll make it further, okay? But again, since that acceleration is still the same, it's still going to be pulled up to that top plate in a given amount of time, right? If I make it, what we're looking for here is the speed that could cause this to happen, that horizontal speed to happen so that it actually clears the plates. Notice again, it's always traveling up, and if you keep your eye on the time up there, it's actually always taking the same time to eventually hit that top plate, which makes sense because it's always starting out from the same initial vertical velocity, and it always has the same vertical acceleration, and it always has to travel the same vertical distance, right? It's just a matter of whether, while it traveled that vertical distance, did it go fast enough sideways that it traveled a large enough horizontal distance to do this and clear the plate. What vertical displacement does it need to move through? Well, it's going to go like that, right? That's the vertical displacement it will move through. How far is that? Careful, it's not quite 1 centimeter, right? This is not down here. It's not traveling 1 centimeter up. It tells us it's at the vertical midpoint, meaning it's halfway between this plate and this plate. So this is only half of 1 centimeter. This is 0.5 centimeters. So there we go. That's the vertical displacement it's going to need to travel through. So 0.05 0.005 meters. And I've already committed it to by making dx positive and dy positive. So I'm just going to go ahead and make sure I clarify that I'm going to call those directions positive in the y-axis and the right direction positive in the x-axis. And that makes left negative in the x-axis and down negative in the y-axis. All right, now it told us it was initially moving horizontally. Diagram suggests that as well. So what is the initial vertical velocity? How fast was it moving up or down at the beginning? Well, it wasn't, right? V initial in the y-axis is just 0 meters per second. Much like our ball from Physics 20, when we threw it sideways off the cliff, it has an initial sideways velocity, but until gravity starts accelerating it downwards, it's not moving downwards, right? At the beginning, this was not moving upwards. Only once it enters the electric field and that force starts to accelerate it upwards did it have an upwards y velocity. Now the final y velocity, we don't know that, right? We could probably figure it out. Maybe we'll need to, maybe we won't, but we don't know it. I'll put a question mark. It's not what we need to find, okay? This is what we were asked to find. We don't know it though, so I'll just put a question mark. Now the acceleration in the y-axis. Here is the one difference between these types of problems and the ones you're used to from Physics 20. Okay, in Physics 20, we knew the acceleration in the y-axis. It was 9.81 meters per second squared, right? Because it was acceleration due to gravity. Here's the one difference. We don't actually immediately know the acceleration in the y-axis, but we do know from Newton's second law that any acceleration is equal to the force acting on it divided by its mass. So the y acceleration will be equal to the net force in the y-axis acting on it divided by its mass. Okay? In this case, the net force is just the electric force. Now, you might be right now having a very good question of, hang on, what about the force of gravity downwards? And I'm glad you had said that in your head, right? I'm glad you asked that because it's true. We maybe should think about the force of gravity. However, if you actually do the calculation, and in the filled in notes that have extra examples, you can see I do the calculation where I include the force of gravity, and it actually ends up being so tiny compared to the electric force that it doesn't make a difference. The other thing about doing that is that, honestly, this question didn't give us enough information to know if that's actually up and that's actually down. Right? This could be a sideways apparatus. We could be looking at it from above, right? So the force of gravity might not even actually be towards the bottom of the page. It might be into the page or even out of the page, right? So the way they've set it up, and to be honest, 99% of the time, this force is so much stronger than the force of gravity that the force of gravity might as well be 0 compared to it. When you add them both up, it doesn't even change the number on your calculator because it's such a small number in comparison that it's down in the hidden digits on your calculator. So all that to say, this is just the electrostatic force divided by the mass of the electron. That will tell us its vertical acceleration, okay? Now we're gonna have to do some work to find that potentially, but let's just kind of make a plan here, right? Like I said, all we're missing to figure out the velocity is the time, but we're never gonna get it in the x-axis because we don't really know much in the x-axis, right? All we know is how far we have to go. What we need to figure out to be able to figure out how fast we're moving is how much time we have to travel this distance, right? And then from there, it's easy peasy. We're back in Science 10 once we get the time. Getting the time is going to be the Physics 20/30 part. All right, so what do we know? We have the displacement. We have the initial velocity. If we just had one more variable, we would be able to find the time because remember, there are 5 kinematics equations on your formula sheet. And each of those 5 equations is set up to work when you don't know and you don't care about finding one of those 5 kinematics variables. Those 5 kinematics variables being these, right? Displacement, initial velocity, final velocity, acceleration, or time. Okay, so this one, for example, acceleration is VF minus VI over time, right? Well, that works really well if you don't know the displacement because you don't have to use it, as long as you don't want to find the displacement because this doesn't contain it, so it won't tell you D, right? So that's not the equation for us here. This one works really well if you don't know and don't want to find the final velocity because it doesn't show up. This one works really well. This one works really well if you don't know and don't care about which one doesn't appear? The initial velocity, right? What about this one? If you don't know and you don't care about finding the acceleration. And this one, if you don't know and you don't care about finding the time, okay? So let's kind of go through here and think about this. With these 5 equations, right, look at all of them. No matter which one of them you look at, if you know 3 of the kinematics variables, you can find a 4th, right? If you know v final, v initial, and the acceleration, for example, you could find the displacement. If you know the time, the initial, and the final velocities, you could find the displacement, right? And we could do that for all of these. So as long as you know 3 kinematics variables in a situation, you can always find a 4th. Well, like we said, we need to find the time in the y-axis to bring it over to the x-axis to finally find the velocity in the x-axis. Right now, we only know 2 variables in the y-axis. We want to know the time. Now, if we look at the acceleration in the y-axis, though, we're on to something here. Maybe, right? If we could get the acceleration in the y-axis, we would then have 1, 2, 3 variables in the y-axis, and we'd be able to find the time, right? We'd be able to use this equation because we'd know the displacement vertically, the initial vertical velocity, and we would know the acceleration vertically if we could find it with this idea here. That would let us find the time, bring it over to the x-axis, and then just use good old v equals d over t to find how fast we'd have to be moving. So let's think about that a bit more. Can we find the vertical acceleration, or AY? All right, well, I mean, we know, right, that the acceleration of an object, whether it's vertical or horizontal, in this case we're looking vertical, so the vertical acceleration of an object will be equal to the net force acting on it in that axis divided by its mass. And in this case, that's just the electric force divided by the mass. Okay, so the y acceleration will just be the electric force divided by the mass of an electron. And we have the mass of an electron, it's on our formula sheet. Now, unfortunately, we do not directly, anyway, know the force that's acting on the electron. But this happens in physics, right? We hit a speed bump and we realize, okay, I don't have that. We've got 2 options. We can give up, or we can say, is there a way we could find that with what we have? Well, we do know that the force acting on any object with charge, right, will be equal to its charge times the electric field it's in. That's just this good equation that we know and love, right? Rearranged for the force. But then we say, oh no, we don't have the electric field. So we can give up, or we can say, do we have the information we need to find the electric field? Well, we do know how far apart the plates are, and we do know the voltage across them, right? We know the potential difference across the plates, and we know how much they're separated by. So hang on a sec. Voltage, distance between them, we can get the electric field, right? So the electric field is just going to be that, right? And we've got the voltage, we've got how far apart the plates are, so we can get the electric field. So we can get the electric force. So we can get the acceleration, right? It's almost like dominoes. You set them up and then they all kind of fall into place. So we could go one at a time and just calculate the electric field, then use that to calculate the electric force, then use that to calculate the acceleration. But let's just kind of put these ideas together here. Let's just say, so the acceleration in the y-axis is the electric force divided by the mass of the electron, right? But the electric force is just the charge of the electron times the strength of the electric field divided by the mass. But the electric field is just the voltage or the potential difference divided by how far apart those plates are. divided by the mass. So I'm not saying you have to do it this way, but it's, it's a good skill to start practicing, kind of putting equations into other equations, right? I haven't said anything that's not true here. The acceleration is the force divided by the mass. And the force is the charge times the electric field. And the electric field is the voltage divided by the separation distance. So this is fine. That means our acceleration in the y-axis will just be the charge of the electron times the potential difference over the distance between the plates, all of that divided by the mass. And we know every single one of those. We know the charge of an electron. It's on our formula sheet. We know the voltage. They told us that in the question, 2,000 volts. We know how far apart the plates are, 1 centimeter. And we know the mass of an electron. That's on our formula sheet. So let's put those all in and calculate the vertical acceleration. Okay, so there we go. Charge and mass of an electron, again, those just come from here on the formula sheet. Negative 1e, mass 9.11 times 10 to the negative 31. Elementary charge, 1.6 times 10 to the negative 19. Okay, and then the voltage was given in the question as 2,000 volts or 2,000 joules per coulomb. And the separation distance was given as 1 centimeter or 0.01 meters. So plugging that all into my calculator carefully, I got that the acceleration in the y-axis would be 3.5126 times 10 to the 16th power meters per second squared. Now again, I know that seems like a very large number, but don't forget, this is a tiny mass, and tiny masses accelerate very easily. And then add to that the electric force is very strong. You've got a pretty strong force acting on a tiny mass. That makes for very large accelerations. So the acceleration of this would be that. We got a positive. Is that a good sign or a bad sign? I'd say it's a good sign, right? We called this direction positive. We got a positive answer. Our force, we would have given a positive sign. So the acceleration being positive, that's a good sign. So we could say it's at 90 degrees if we like, right? Meaning towards the top of the page like this. You could say up, I guess, but again, we don't really have enough information to know if that's actually up, right? We don't know the orientation of this apparatus. All right. Now, don't lose sight of the game plan here, right? Remember the plan we set up. We were going to find the acceleration, because then if we had the acceleration, we would know 3 variables. And with any of our kinematics equations, if we know 3 variables, we can find a 4th. So if we can find the time in the y-axis, we can bring it to the x-axis. And in the x-axis, it's just uniform motion. So we can use v equals d over t to find the time. So let's now do stage 2 of our plan, which is we've got displacement vertical, we've got initial velocity vertical, and now we have the acceleration vertical. So we can find the time in our y-axis. Looking at our equations, which one looks like the right one? We have d, vi, a, and we want t. Give you a second to look here. d, vi, a, t, right? We need an equation that has all of that stuff and nothing else. It needs to have t so we can find t, and then the other things it has we have to know. Couldn't use this one because we don't know v final, right? Couldn't use any of them because we don't know v final, right? That's the only one for us here. So step 2, we're going to find the time, right? Now, I'm working in the y-axis. I might just use black here, though, and drop the color coding. Otherwise, this will just become a big red blob. So we're going to find the time, okay? Write down the equation that we're going to use, which is that the vertical displacement will be equal to the initial vertical velocity times the time plus the acceleration in the y-axis times the time squared over 2. Okay, now, what's even better about this is, hey, our initial y velocity is just 0. So, I mean, we could keep it in the equation if we want, but it's 0. Why bother? So really, we just have this as our starting point. So let's now solve for time. Okay, we'll multiply both sides by 2, divide by a. That'll give us that the time squared equals 2 times the vertical displacement, dy, divided by the vertical acceleration, ay. And the last thing to do, we don't want t squared, we want t. So the opposite of squaring is square rooting, and here we go. This should give us the time. So let's put in our numbers here, okay? We'll think about direction. I called this the positive y direction. Since it is moving in that direction, its displacement is towards the top of the page, I will make this a positive dy. This is why it's nice to have your givens organized into this table so they're nice and easy to reference when you need them. So 2 times positive 0.005 meters over our acceleration. And again, that acceleration, because the force is this way in the positive direction, our acceleration should also be positive. So I'll put that number we calculated in stage 1 in here. And then calculating that all out, I got that the time it would take to travel that far vertically is 5.3356 times 10 to the negative 10 seconds. A very short amount of time, but this is a very fast acceleration and it has to travel half a centimeter. So not surprising that it takes an incredibly short amount of time to actually crash into that plate, right? So if you were to just hold this electron here and then let it go, it would take about half a nanosecond to actually crash into that plate, right? Less than 1/1000th of a second. Makes sense though. Very strong force, very small mass gives us very big acceleration, so it wouldn't take much time. All right, now it's exciting. Okay, now we are back in Science 10, because if I told you in Science 10, hey, something needs to travel this far, and it has this much time to do it, could you calculate how fast it would need to be moving? Sure you could, right? If it's uniform motion, we just need to do V equals d over t. And it is uniform motion once again because there's no acceleration horizontally. No force is causing it to get faster or slower in the x-axis. So we are now there. Step 3, we are going to actually calculate the horizontal velocity it would need. So that means that the horizontal velocity, how far does it need to go? Well, it needs to travel 2 centimeters, right? Like we said, if it can go that far in this amount of time, it will be able to have cleared the plates before it's crashed into the top plate. Because this is the amount of time it will take to crash into the top plate, right? That's what we just calculated here. So now we know it just needs to go horizontally 2 centimeters in that amount of time. So I got that it would need to be traveling at 37 million meters per second. So 2, how many significant digits do we get here? Looks like we get 3, right? 3. We use the charge of an electron, that's also 3. So 3 significant digits, this would be 3.75. Careful, that 4 gets rounded up to a 5 because it's followed by an 8, times 10 to the power of 1, 2, 3, 4, 5, 6, 7. 3.75 times 10 to the 7 meters per second. Okay, so there we go. We figured it out. If it were moving that fast sideways, it would travel 2 centimeters sideways in the time that it would take to travel this far, half a centimeter, vertically, based on the forces involved and therefore the accelerations involved, right? And that's the logic we just followed through there. Okay, now I want you to notice this is no different than the projectile motion ones you did in Physics 20. The literal only difference is that in Physics 20, you knew the acceleration was 9.81. So there's one extra step here in Physics 30. You have to first find the acceleration by using another idea from Physics 20. The acceleration of an object is equal to the force acting on it divided by its mass. And finding the force is really the Physics 30 part, right? Here is the part of this question that is from Physics 30. That step right there. Other than that, Physics 20 projectile motion. Isn't that cool? Fun fact, by the way, this is about 10% the speed of light, a little bit more than 10% the speed of light. So if this were a university class, we'd actually have to redo this question and allow for relativistic effects because some weird stuff would actually be going on with the electron. It would be experiencing time and distance a little bit differently. Anyway, I'll let you find that out on your own in university or through your own research. All right, okay, so there we go. Let's try this one out. All right, so it just asks, in the above question, 3 students calculated the electric field between the horizontal plates in 3 different ways. 1, 2, 3. Comment on the validity of each calculation. So let's look at student 1 here. Clearly they're all using, the correct formula for the electric field, potential difference over the distance between the plates. Well, I should say between the distance between the 2 points we're comparing. Okay, that might be between the plates, but it could be different as well. So these students have used 2,000 volts and a distance of 0.01 meters. So they've used the entire voltage, and then they've used a distance of 0.01 meters, which is just 1 centimeter. So they've used the whole voltage across the plates, and they've used the whole distance across the plates. Is that okay? Well, yeah, in fact, that's what we did, right? So that's fine. They've used the entire potential difference to go all the way across the plates and the entire distance across the entire plates. So yes, this totally works. Nothing wrong with that. What about these students? They've used 1,000 volts, which is half of the potential difference. And they've only used half the distance. You can actually see why they might do that, right? Because the electron started halfway, so they might have just been thinking about it that way, right? Let's just think about the voltage from here to here instead of all the way across the plates. Now, is that okay? Can they use half the voltage if they only use half the distance as well? Well, yes, right? Because the voltage is the potential difference. And so the amount of potential energy a charge would change by for going from here to here is just half of going from here to here because we're in a uniform electric field. So yeah, that's totally okay. If you use half the distance, you just have to recognize that the potential energy change involved in that is half as large. So yes, these students are also fine. All right, what about these students? They use 2,000 volts, so they use the entire voltage all the way across the plates, but then they only used half of the distance between the plates. Is that all right? Well, if the voltage across the plates is 2,000 joules per coulomb, the change in energy per coulomb of charge that you have will be 2,000 joules by going from here to here. Will it still be 2,000 joules if you only go halfway across? No, right? I mean, if you think about it in terms of gravitational potential energy, would the change in energy of a ball being lifted from here to here be the same as the change in energy of a ball only being lifted halfway? No, it would be half as much, right? So that's the fact that it would be half as much is why this one was okay. And it's why this one is wrong. They've used the entire potential difference all the way across the plates, but they've only thought about a change of distance of halfway across the plates. So no, this one does not work. All right, one last example. It comes from an old Physics 30 diploma. Let's try it out. So like I said, often a good idea to read what we're finding first, read the question before diving into the information, just so that we better know what we're looking for. So based on our measurements, the strength of the uniform electric field in the region expressed to 2 significant digits is blank newtons per coulomb. Okay, so we're looking for the strength of the electric field. We're trying to find what is the electric field strength. All right, so let's start taking a look at the information here. So a beam of electrons, okay, so electrons again, is incident on a region containing a uniform electric field as shown below. All right, the electrons in the beam each have a speed of 4.5 times 10 to the 5 meters per second. While in the electric field, the electrons accelerate towards the top plate. All right, well that makes sense. The top plate they're showing is positively charged. We know an electron would be attracted to a positive because opposites attract. Right? So what we're trying to find, the electric field would be like that, right? I won't draw it in everywhere. It might get, well, I can draw it in most places. Okay, the electric field would look like that. Again, what would a positive feel? The electrons deflected up. Makes sense that the electric field would be down then, okay, because electrons are negative and electric field direction is defined as how a positive would feel a force. Now, we know that the electrons have a speed of 4.5 times 10 to the 5 meters per second. Now notice they came in horizontally. So that is a horizontal velocity, right? That's a Vx. And again, is there going to be any x force that's accelerating these things horizontally? No, right? In the x-axis, we have uniform motion. X-axis is described by physics principle 0, right? Uniform motion. V equals d over t. Now that's completely separate from what's happening in the y-axis where there is accelerated motion because there will be a force acting upwards, or at least towards the top plate, on these electrons. That's what's causing that acceleration vertically. So that horizontal motion and that vertical motion are entirely separate from each other, right? So just like you would do in Physics 20, we'll keep them separate from each other. We'll split up our X and our Y axes and we'll analyze the motion in them separately because it's two different kinds of motion completely, right? This force has nothing to do with this horizontal motion. It's entirely acting on the vertical properties of its motion. Now, the horizontal distance that they travel, they didn't directly tell us it, right? But notice it tells us we will need to take measurements on this diagram, right? Our answer is based on our measurements. So this is a question from the diploma, and the diploma has done this from time to time, right? They're just testing, do you know how to take the measurements? Do you know which measurements you would even need, right? So you actually would pull out a ruler and measure this distance horizontally, okay? You would actually physically measure it. So when I did that, it might be different. Like if you've printed out the notes at home and you're trying this yourself, don't panic if you're getting something different than me. But when I did it on my piece of paper, I measured this with my ruler to be 4 centimeters. So horizontally, these electrons traveled a distance of 0.04 meters, right? Divide by 100 to convert to meters, okay? Horizontally. Now again, it's uniform motion in the x-axis, so we can just use v equals d over t. We know their horizontal velocity, we don't know the time. However, we do know, once again, that it's the same as the time in the y-axis, right? However long they took to do this horizontally is the same amount of time they took to do this vertically. They didn't split into two different particles somehow and take different amounts of time to go up as they did to go left. Now, moving over to what we know in the y-axis. In the y-axis, can we just say v equals d over t? No, right? Because what v? At first, it has a y velocity of 0. It was moving sideways, not up or down, right? So there's no such thing as vy. There's an initial y velocity, there's a final y velocity, but the y velocity is constantly changing. So we're going to need to use all 5 of our kinematics variables for non-uniform motion. And those are, again, displacement, how far it went, initial velocity, how fast it was moving at the beginning, final velocity, how fast it was moving at the end, acceleration, how much its velocity was changing each second, and the time, right? If you ever forget them, they're all on the formula sheet, of course. You just need to look at the kinematics variables and take note of them, okay? All right. Now, what do we know in the y-axis? Well, how far did it travel vertically? Again, they didn't tell us, but they told us we can take measurements. In fact, we need to take measurements on this diagram. So we would pull out our ruler and see, okay, how far did they travel vertically? Now, when I did that with my ruler, I got 1 centimeter. Again, yours might be slightly different due to printing differences, but that's what I'm getting. That would be 0.01 meters. Okay, I've already done it once again by listing those both as positive, but I'm going to go ahead and define this left to the left side of the page as the positive x direction because that's the way they're moving, so I might as well have positives rather than adding negatives, and I'll make towards the top of the page the positive y direction. Just a side note as well, don't let this question make you think that every single question on the diploma can be solved by measuring stuff directly on the diagram, okay? They explicitly state this when that's the case, right? Often their diagrams aren't actually to scale and you can't get the measurements with a ruler, okay? But anyway, let's jump back in here. What is the initial y velocity? Well, how fast are they moving up or down initially? Well, they're not, right? They were moving sideways. So VIY is just 0 meters per second. Their final y velocity, we don't know it, but maybe we never need to find it. The acceleration in the y-axis, again, here's the one thing that's different from physics 20. We have to find that with Fy over the mass, right? We know the mass of an electron, okay? So there's the difference, right? In physics 20, we would know it was just 9.81 because the only reason it was accelerating vertically was because of acceleration due to gravity. Now it's because of an electric force, so we'll have to calculate that acceleration if we need it. And time, we don't know it, but we know it's the same as whatever time is in the x-axis. All right, so let's see if we can kind of make a plan here, right? We want to get the electric field. Now, the electric field we know is closely related to the electric force, right? In fact, if we had the force, we could get the electric field because we know the charge of an electron. And the electric field is just equal to the force acting on a charge divided by that charge, right? So if we had the force acting on the electron, we would have the electric field. Okay, so we need to find the force acting on the electron. Well, we also know the mass of an electron. And so if we had the acceleration and the mass, we could find the electric force that's acting on the electron. And again, with the force, we could find the field. Can we find the acceleration here? Let's take a look. We've got the displacement in the y-axis, the initial y-axis velocity. We don't have the final. Oh, we only know 2 variables in the y-axis. Remember, if we know 3 of the kinematics variables, we can use one of these equations to find a fourth. So if we only knew one more of these things, we could find the acceleration and therefore find the force and therefore find the electric field, right? So our situation right now is this. We need the force on the electron to find the electric field using this equation, right? We know the charge already. If we just had the force, we'd have the electric field. But to find the force, we would need the acceleration, right? With Newton's second law, acceleration is equal to the force divided by the mass. So the vertical acceleration is equal to this vertical electric force divided by the mass. But we don't have the acceleration. So to find the acceleration, like we said, we would just need one more kinematics variable because then we would have 3 and we could find the acceleration with the appropriate equation. Well, what about time? Do we have enough information in the x-axis to find the time? If I told you, even back in Science 10, hey, I walked this far and I was moving this fast, how long did it take me? Would you be able to figure it out? You absolutely would, right? So there we go. There's our plan. We can find time here, then bring it over here, and we'll know 3 kinematics variables. That will let us find the fourth, acceleration, and then the dominoes all fall into place, right? With acceleration, we can find the electric force. With the electric force, we can find the electric field, right? So we'll find the time. We'll use that to get the acceleration. We'll use that to get the force. And finally, we'll use that to get the electric field. So let's jump in. Here we go. Execute the plan that we've just set up. Step 1, we need to find the time, and we'll do that in the x-axis. Now, as we said, in the x-axis, right, it's uniform motion. There's no change in its velocity here because there's no horizontal force. So we can use the uniform motion equation, v equals d over t, right? And really here we're applying physics principle number 0, that if the net force on an object is 0, it's moving with uniform motion, right? V equals d over t. Okay, so rearranging this a bit, we'll multiply both sides by t to get it out of the denominator. Divide both sides by vx to solve for t. And so the time can be found by taking the distance it traveled horizontally, which we measured with our ruler to be 4 centimeters, and dividing it by its horizontal velocity, which they told us was 4.5 times 10 to the 5 meters per second. So there we go, put those in, just be careful, don't forget to convert centimeters to meters, right? Centimeters wouldn't cancel with the meters per second to give us units of second. Anyway, when I did that, I got that the time was 8.88888, repeating, so the last one will just make a 9 because it's followed by an 8, times 10 to the negative 8 seconds. Again, definitely keep your unrounded answer. We know we're going to use this number again, so we don't want to use the rounded one, okay? All right, so our plan is falling into place. We've now got the time. We know that means we should be able to find the acceleration if we choose the correct equation. Because in the y-axis, right, again, we use the x-axis to find the time, but it's the same time in the y-axis. So now look at what we've got. We've got the vertical displacement, the vertical initial velocity. We want the vertical acceleration, and we have the vertical time. So we're looking for an equation that contains d, vi, a, and t. Let's go to our formula sheet and see if we can find it. something that has D, VI, A, and T. Hey, same one we used last time, right? This will tell us the acceleration if we know the time, which we do, the initial vertical velocity, which we do, and the vertical displacement that it's going to travel through, which we do. We measured it from the diagram. So we're ready to go. All right. And once again, it's our lucky day, the initial vertical velocity is 0 because the beam was moving sideways, not up or down. So the initial vertical velocity, or VIY, is just 0. So that leaves us with this. Let's now solve it for the acceleration. So we'll multiply by 2 because it's being divided by 2, and then divide by t squared because it's being multiplied by t squared. So we'll cancel those out. What we do to one side, we must do to the other. And we get that the acceleration in the y-axis is equal to 2 times the y displacement, the vertical displacement. Well, we measured with our ruler that to be 1 centimeter. Don't forget to convert to meters, right? But there's 100 centimeters to make 1 meter, so we need to divide by 100. So 0.01 meters divided by the time squared, which is what we found in step 1, right? That's why we needed it before we could move on. So divide by that time. And don't forget to square it. Common student mistake here is to forget the square. Not that they don't know it's supposed to be squared, but they just kind of just forget about it after this long into a problem. Okay, so let's go ahead and calculate that out, and we'll have our acceleration, and we'll be on our way to executing the next stage of our plan. So when I did that, I got 2.5312 times 10 to the power of 12 meters per second squared. So that is its acceleration vertically in the y-axis. Okay, so now here we go. We got the acceleration now. Now we can get the electric force using the fact that the acceleration is equal to that force divided by the mass of the object it's acting on, which is the electron here. So here we go. All right, and so here we're just using Newton's second law, right? Physics principle number 1, accelerated motion. I guess we were actually using that in the previous step as well. We were thinking about accelerated motion, right? Motion where the speed is not constant. It's changing its velocity, okay? But Newton's second law, just an equation. The acceleration is equal to the net force divided by the mass. In this case, that net force is just the electric force. That's what's acting on the beam of electrons to change its motion. So if we multiply both sides by mass, we get that the electric force will be the mass of an electron times the acceleration that it's undergoing, which is what we just found, right? What's its acceleration if it had went through this displacement in this amount of time starting from rest, right? We found that. So we have the mass of an electron. It is on the back of our formula sheet, right? 9.11 times 10 to the negative 31 kilograms. So here we go. Multiply that mass by the acceleration we just found in the previous step to get that it must have been experiencing a force of 2.3059 times 10 to the negative 18 newtons. And we're so close now, right? If we know the force that an electron felt, right, and we know the charge of an electron, we can figure out what the strength of the electric field it was in must have been. Because the electric field is just the force divided by the charge, right? How many newtons of force will a charge feel per coulomb of charge that it has? Well, we know how many coulombs of charge an electron has. It's on the back of our formula sheet. So we're at the final stage of our plan here. We are going to now find the electric field, which is what we need to answer this question. So we now know that the electron felt a force of 2.3059 times 10 to the negative 18 newtons. And it has a charge of, again, from the back of your formula sheet, negative 1e, and e is just 1.6 times 10 to the negative 19 coulombs. And here we go. I got that the electric field would be 14.411875 newtons per coulomb for all of the stuff to happen the way that we've, calculated it out here. Okay, so I mean, it is a vector, so we could give a direction, although for a numerical response here, they're not going to look at that. But it would be, we could say towards the bottom of the page or towards the negatively charged plate, right? Again, we figured that out at the very beginning because electric field direction is defined as the direction in which a positive would feel a force. Now, they asked for our answer to 2 significant digits. 2 significant digits. So that would just actually be 14 newtons per coulomb. If we were actually writing this diploma, we'd go to our answer sheet, and for number one, we would fill in 14, right? Only 2 digits. We don't need the last 2 boxes. That's okay. You always start in the leftmost box. If you don't need any once you're done with your number, that's okay, right? Always left justify. And there we go. Now, number 2, here's one of those classic diploma questions that they do like to ask, okay? Basically, what they're doing with these is testing to see, are you thinking about like the physics? Do you understand the physics involved here? Or did you kind of just memorize an approach, right? In physics, we should really never memorize. We should just understand the underlying concepts and then apply them here. So that's essentially what they're testing here. So what did we use here? I mean, we happened to write them down as we went, but like, how did we know we could find time with V equals D over T? We wouldn't have known to do that as physics students if we didn't understand that without a force acting on them horizontally, these won't accelerate, right? And therefore, they're undergoing uniform motion, and therefore we can just say that the distance they travel divided by the time is their speed, because their speed's not changing. It's a constant speed. So we are applying uniform motion there, Newton's first law, right? From the back of our formula sheet, that is physics principle 0. We know that if the net force on them in the x-axis is 0, then they will not accelerate, and we can apply V equals D over T. Do you see what I mean, right? What guided our calculation there? We would not have been able to start this without recognizing that. Okay, it's not that the other physics principles aren't true. Was energy conserved here? Absolutely. But at any point, did we say total energy initial equals total energy final and rely on that to get our answer? Right? Was momentum conserved here? Absolutely. It always is. It's a law of physics. But did we ever say to get our answer, total initial momentum equals total final momentum? Do you see what I mean? We didn't actually really rely on those physics principles. Though we trust in them and we know they're true, we didn't rely on them in this context to guide our calculation and analysis, right? Next, we moved on to the fact that, I mean, both of these here, right, especially this one, we're using the fact that if there is a net force acting on an object, it will accelerate. And that acceleration will be directly proportional to the force and inversely proportional to the mass, right? Here as well, we're relying on analyzing non-uniform motion. So what physics principle is really guiding us there? Physics principle 1, accelerated motion, okay? Was charge conserved here? Once again, was charge conserved? Yes. But did we use that? Did we use the fact that charge can't be created or destroyed to guide our calculation here? No, right? So I would say we used 0 first, and then we used 1. Physics principle 0, physics principle 1. And this goes back to what I was saying. Why do they have these numbers on the back of your formula sheet? It's just so they can ask stuff like this, right? So you can easily give a number to reference the physics principle that was used. If you asked a student from BC, hey, what's physics principle number 4? They wouldn't really know what you were talking about. This is just an Alberta education thing to give some important ideas numbers so that you can easily reference them. And you should reference them throughout your work, right? It never hurts to say, I'm applying this physics principle. Lets us understand where you're coming from. So for this one, if we were writing the diploma, we would say 0, 1, bubble in the 0, bubble in the 1, and there we go. Done. 2 marks really for 1 question, right, on the diploma. 1 for this, 1 for this. Granted, this is a bit of a longer, tougher one, but still, 2 marks, 1 question, not bad. Alrighty, so go ahead and try this one out from your formative assignment. Of course, you can also now do the other one from your formative assignment. This is the end of the lesson anyway. Okay, that's page 574, number 2. Short formative assignment. It's just a couple of these kinematics and dynamics within an electric field type questions, okay? So try those out. As always, my solutions are posted. The textbook solutions are posted. If you get stuck and you just need a push in the right direction, you can consult those. Of course, as always, do not hesitate to reach out to me via email or booking a meeting or whatever. I'm always happy to help. Okay, but that wraps up chapter 11, lesson 3, and therefore that wraps up chapter 11. So once you've done your practice, you've, asked your questions and all that, you are now ready to write the chapter 11 quiz. We've got one more chapter, chapter 12 for unit B, and then we will be done with our second unit. Hard to believe. All right.